Hello all. I'd like to make some comments on slides in chapter number 1. In chapter number 1, certain aspects, very general aspects of computers will be discussed. One of them is the difference between computer organization and computer architecture. Some units of measure popular in computer systems, frequency, time, volume of memory, some of the examples. A couple of remarks on the evolution of computers. Okay. Very important computer layered system, modular system, from very low to very high, where on the very low level we have hardware, basic logic gates, and on top we have the users. A couple of remarks on von Neumann architecture. Important, historic, very important architecture invented by von Neumann, by the way, Hungarian mathematician who joined the Manhattan program in the US and became quite a productive computer science person. So we have a distinction between computer organization and architecture. There is plenty of reasons to study both organization and architecture, probably the most important for designers of computers, designers of computer systems, because we have aspects of system software, we have many aspects of computer hardware, question of time, space, and trade-offs in between, by the way, including price as well. So we have very important principle of equivalence of hardware and software. Please remember this. It's very interesting, surprising maybe sometime, but very interesting, very important, that any task done by software can also be done using hardware. Okay? And vice versa, whatever can be done on hardware can be performed on software. And one important remark, speed is not a concern here. You can easily conclude that obviously performed on software is slower than the tasks performed on hardware. What are the computer components? Well, in general, referring to very basic von Neumann architecture, we have a processor, we have memory, we have input-outputs, of course, and we have certainly mechanisms of transferring data from one to another and to the outside world. And this is very simplistic, very simple graph picture of von Neumann architecture. Surprisingly, memory is in center rate, so not CPU. We have two arrows between memory and CPU. Okay, we send instructions to CPU for execution, and we send back results of calculation to memory. Before we start thinking and using the computer, we have to enter the program and data. This is why we have one arrow, single arrow from input device to memory. Once we want to communicate with the outer world, we send it to the output, outside world through the output device. So we have one arrow from memory to out. And then we have secondary memory, and we have two arrows, which means we can save data and programs in the secondary memory, and then we can retrieve it. So once the program is done, we can save it for later on. Once we have certain results, if we think to use them later on, we send them to secondary memory for later use. We have very specific examples of computer system with very specific of hardware, so take a look on it. We have a certain set of units as well. Here, let's take a look. So K, capital K, it's kilo, okay? But it's capital K. Lowercase k, it's a prefix being used in physics, little k, as 10 power 3, okay? Sorry, it's, yes, 10 power 3. But K, capital K, is kilo. In computers is 2 power 10. It's very close, okay? It's a little bit more than 1000. It's a little bit more than 10 power 3. 10 power 3 has 3 zeros. 2 power 10 is 1024. So you pay for kilo, but you get 24 more. Mega, capital M, giga, tera. Very rarely use petabytes and so on. The biggest, practically the biggest we use right now is tera, like terabytes in a hard disk, 2 power 240. Important in computer hardware is CPU frequency, where 1 megahertz is 1 million hertz. So now processor speeds, well, speeds in quotes, frequencies are measured in megahertz or gigahertz. Again, 1 kilobyte, for instance, is 2 power 10 bytes, which is 1024, okay? 2 power 10. 1 meg is 1000 times 1k, and so on. Differences 2 power 10 from each to other. Main memory is RAM, random access memory, is very often measured in gigabytes so far. Obviously, hard disk may have terabytes, very popular right now. For the space, the prefixes are well known: milli, 10 power minus millimeter, micro, 10 power minus 6, and so on, nano, pico, femto, very rarely being used in electricity, in electronics. Pico, yes, the most popular pico prefix is being used in capacitors, picofarads, for instance. Femto, rarely met, okay? Millisecond, 1000th of a second, and so on. Obvious prefixes and import. There is certain relation that you have to remember between the cycle time of periodic physical entities. So if we have a periodic physical entity, like voltages, currents, and so on, such periodic physical entities have the cycle time. Let's call it T, capital T. And closely related is a frequency, is a reciprocal of T, 1 over T, T power minus 1. So the bigger is the cycle time, the period, the T, capital T, the lower frequency is. Example of recalculation of the time and frequency is given below. So if the cycle lasts 7.52 nanoseconds, it is 133 million of hertz. A couple of very specific hardware examples, just take a look on it, in which, by the way, on the first place there was frequency of CPU 3.6 gigahertz. You can recalculate it into the cycle time period of this clock. So we have random access memory. It doesn't mean accessible in random. No, it means that whatever location of the memory you choose, you have the access. Uh, in some older memories, external memories, tape memories, for instance, the access was not random. To access to the data at the beginning, or let's say at the end of the tape, you have to rewind the whole tape to have the access to this memory. Obviously, random access memory we have made on the integrated circuitry right now. You can enter any location of the memory at any time. You can choose randomly whatever address you have to access, you do access, okay? There is another type of memory, it's a cache. It's coming from French cache. Cache means hide. It's a certain intermediate memory between internal memory, very fast, and slower memory. So cache memory can be accessed pretty fast. So the cache memory is in between CPU registers and RAM memory. It looks like making notes while reading a book. If you want to have fast access to certain pieces of information and you don't want to page the whole book, you write it down on a side. It's much faster than accessing the book. By the way, accessing the book is much faster than accessing other books you have in the library, right? Library is like external memory, hard disk. The book is like a RAM, and then you have cache, which is a little bit faster than accessing the book, the book accessing the RAM memory. So we have different types of memories. You obviously will learn, or you already did learn it in the digital systems. Take a look on it and just remember it does exist. Very specific pieces of hardware. Take a look on them. An example system in the, all computer systems, you may access the data through the serial ports, which means you have to access one after another piece of data or even bits, while when you have parallel ports, you may access the unit of data, like maybe the bytes at a time. So in serial ports, data accessed and sent in series of pulses, one after another, bit by bit. Parallel ports sends and receives several bits at a time, typically 8 bits at a time. And what's the difference? The difference is certainly in speed. Parallel is 8 times faster than serial port. The question is, why don't we use parallel ports or parallel data in all situations? That difference is big because the cost of copper or aluminum wire, single wire, is one wire is cheaper than 8 wires being sent. So very often on long distance, if we insist to use the hardwired connection, the serial method of sending the data is much cheaper. So the question, why don't we use serial connection in all situations? Well, when the distance is shorter, for instance, inside of computer, we send and we use a parallel method of sending the data, and we have buses sets of 8 or 16 or even more wires, and we send the bit at the same time, faster, much faster, and it's not that expensive because distances in computer are pretty small, pretty short. We have also universal serial buses, plug and play method of setting the communication. So you have examples in this case, in this specific computer. You have a couple of informations about standards organization. One of them is IEEE, Institute of Electrical and Electronic Engineers. They set standards also for teaching computer science in the world. And our program at our university has been set following recommendation of Electrical and Electronic Engineers organization. There's also IEEE organization, well, ANSI organization, which is setting the standard, but mostly on the hardware. Also, you remember ISO standards practically on everything. You may remember ISO when you use the camera. You have the sensitivity set up by ISO organization. Interesting is the historical development of computers. What is not mentioned here is probably one of the most popular and the oldest computers, which is Abacus, right? But coming back to more interesting solutions, the first attempts to build computers reaches the 16th century. And then 18th, 19th century. What is interesting? Interesting is that certain solutions being applied in mechanical machines and in very simple electric machines, electric computers, have been adopted in modern computers. For instance, the question of representation of negative numbers. So ones complement and twos complement. In mechanical machines, it was very difficult to subtract the numbers when the borrowing happened. Mechanism of borrowing is a little bit complex, and it was making the machines pretty complex, then expensive, and then less reliable. So they invented a method like ones complement, twos complement to substitute negative numbers by with certain simple methods. And this method allowed us to avoid borrowing and allowed us to simplify the construction of mechanical machines. It's been adopted by electronic contemporary computers. The twos complement has been adopted, and we will cover in details this method because the calculation was much faster, and this was the reason. More specifically, reaching the hardware of computers, the first electronic, not electric, but electronic machines have been using vacuum tubes. Also, the radio sets have been using vacuum tubes, right? So we have anode, cathode, and we have in the middle, we have another electrode, and this inner electrode is controlling flow of electrons between anode and cathode. So it was something in computers, it's happening on-off, in on-off regime, which means the electrons either passing or not passing, so which is very similar to mechanical switches like light switches. Then after even using vacuum computers, a technology, the first electronic computer was ENIAC. What is interesting that ENIAC in 1945 was using hardware in order to make programs. Entering, there was no input device. We had to change the hardware of the computer in order to make a program. So this was a question of creating a huge board with plugs with wires, and several people were plugging, reconnecting, connecting between logical gates with physical wires. So which was pretty boring, pretty time consuming, and not very universal way of entering data and programs. We were not able to save it. The person who entered the input and output and suggested the using memory was von Neumann. We will talk about this guy later on. A huge revolution in the computer hardware happened in the 50s when the transistors have been created and invented. I remember that PDP-1 and then PDP-10 have been introduced at the universities, and they were very fast and relatively cheap and small. Those vacuum tubes, I remember, super big computers, vacuum tube computers have been used in schools, in universities in 70s, even in 80s, but the area occupied by the computers was a question of a big room, and they did require air conditioning as well. By the way, the first bug name of the error comes from this technology. Then in third generation, the integrated circuitry have been used, and ICs are a different scale of integrations. We have the question of a small, low scale of integration, medium and large scale of integration, depending on how many transistors are being used. Now we may have very large scale of integration, which is using over 100,000 transistors. What is important in minimization is first of all is the size, of course, and then lower consumption of the power, and then those which use less power, electrical power, do not require air conditioning. Although, unfortunately, right now we have to use fans with very fast CPUs right now. But this is the other reason. Later on, the VLSI computers have been created, and VLSIs are using much more than 10,000 components per chip, transistors, hundreds of thousands, and they allow to create microprocessors. The first 4-bit microprocessor was Intel's 4004, not being commercialized, being used in laboratories rather, but later versions of Intel were 8-bit computers, 8008, which have been already used in PDP computers, and then 88, 86, 8088, 16-bit followed the first microprocessor. They refer to Moore's law about integration, scale of integration, but it's not necessarily holding till now. It's changing. So those laws are interesting, but not of very important importance in computers. What is important in computer hardware and software is level hierarchy. So when we look at this picture, you can see that that we have layers. On the bottom of the level hierarchy, we have digital logic, gates. Then we have control, CPUs, use control systems, use control elements, machine level software. Then we have system software, operating system, and so on. We have system software may be written in assembly language, but also in high-level language. So the location is symbolic. Above system software has assembly language. Assembly language is very similar to machine language, but instead of having in machine language level 2, we have binary representation of instructions and data, 0 1s, maybe 8-bit machines, or 16, or also all of them 0 1s. In assembly language, every instruction has its literal representation, easier for human to remember and easier to write down such programs. You don't have to remember everything, every 0 1s combinations. You have assembly language self-explanatory. However, because the computer needs to execute the program, needs to have the program very low, very close to digital logic, must be in machine language. But if we enter assembly language program, such a program must be translated into machine language, and we have assemblers to do it. Above assembly language, we have high-level languages, C++, Java, Fortran, Pascal, and so on. EZ for programming, very powerful. One command, one instruction in machine language may perform several assembly language equivalents of assembly language programs. Important is level 6 users. Users means creating the computer which respects variety of users, not only professionals, but also very average user. Thanks to including the level 6, Macintosh and those using GUI, graphic user interface, probably won on the market. We still have Unix without the graphic user interface. Unix is still the most popular operating system without graphic user interface, although there is plenty of variation of Unix with graphic user interface, but the only reason Unix is still the most popular operating system is fact that we have a huge library, so allowing to solve almost all kind of problems. However, such machines like Macintosh and similar using graphic user interface won the market because they became very popular, thanks to respecting users, including users. Certain brands of computers won the market because of popular approach. And we have some more. Important is here, and we will cover also those aspects, control level. So certain CPUs may be hardwired, frozen, I would say, not easy to change. Certain CPUs are microgrammed. So at the level of my microprogramming, we have specific languages, is microprogramming, which is setting CPU the way to perform a certain architecture of the computer. So we have the choice. The designers of computers have the choice, make CPUs hardwired or microprogrammed. So this is level 1. One level above digital logic gates, logical gates. So level 0 is the lowest level. Like in the human body, anatomy, it's at the lower level. So we have gates and wires. What is interesting in gates, computer gates, we do not have arithmetic gates. We do not have uh, uh, gates which would perform addition, subtraction, and so on. Um, Amazingly, at the level of Boolean algebra, G can perform arithmetic operations. Among them, XOR gate. XOR gate performs addition, arithmetical addition. And I would say, thanks to XOR, we don't have to create arithmetic gates. We may use very, very low level just logic gates and do everything, logic and arithmetics. This is very interesting. Coming back to the history, a few remarks about von Neumann model. And again, ENIAC was created without using von Neumann concept. Von Neumann has introduced its concept in which we have central processing unit and we have memory. Important is memory, that instead of modifying the computer using the hardware, programming computer using the hardware, we can enter electronically. We can enter the programs and save it in the memory. In von Neumann, what is important to remember that von Neumann model is sequential instruction processing, which means we cannot process two instructions at a time, which happens in multi-processor systems. We cannot executing next instruction before having ended previous instruction. So this sequential instruction execution is called von Neumann bottleneck. Okay? This is a limitation in speed in von Neumann machines. And again, von Neumann architecture. So we have one CPU, we have memory, of course. Instead of modifying hardware, we may enter through the input device, we may enter memory, save it, and then execute it. Which wasn't. This is an example of processing certain programs in von Neumann machine, but in another place you have, I think, a little bit simpler and a little bit more clear explanation how the program is being executed. Just look at another presentation in chapter number 1. Obviously, we have non-Feynman models, shortly non-Von models, in which we have several processes which execute several instructions at a time. Right now, supercomputers may have up to hundreds of thousands, if even millions of processors, which obviously complicates operating system, but it makes those computers very, very fast. Below supercomputers, we have multi-core architectures in which several CPUs execute specific tasks. A very typical processor is arithmetic processor, which executes all arithmetic operations. So this would be all about chapter number 1, and thank you all.